There we go. Cool, yeah. Did you have any specific questions for me?
Um, yeah.
What's that?
So, when we're doing hexadecimal,
Yep.
um, it showed like a method. I can't remember. Like how to add or subtract it. Yeah.
Well, for adding and subtracting hex, it's the same way we do for binary, or very similar. Um, so let's start with addition, I guess. Just like you would in any base, you go column by column, and then if your result can't fit in the base's place value, you have to carry over to the next place value. So, for example, this is base 16, so if we get a result 16 or higher, we have to carry that over as a 1. So if you're doing hex 7 plus 9, that would be the number 16, and that means that it exceeds our base. That means we have to carry over. And so when you carry over, that carries over 16, and because this result was 16, there's none left over to remain in that place value. And so then you continue on like that. So for this next one, we have b, which in decimal is 11, and then 11 plus 3 is going to be 14, and then 14 plus 1 is 15. And in hex, that would be f. And then for the last column, we have hex a plus hex 7. A is like 10 in decimal, and when we take 10 and add it to 7, we get 17, which again is too much for this place value to hold, so we carry over the 16, so we carry over 1. And because we took away 16 to carry over, there's 1 left over from that 17 we originally had. And so our result would be hex 1, 1, f 0. And that's like the general process for adding hex numbers. Was there a particular example you wanted me to go over, or?
No, I think the general was good because I've noticed that a lot of our homework is we're initializing our integers as a hex digit, and so yeah, just being able to convert it to like hexadecimal and to decimal to my head, I think it would probably be I guess a challenge, especially during the test.
Right. Yeah, I get what you mean, for sure. Okay. Shauna, you came in. Did you have any questions for me?
No, nothing in particular.
Okay, just making sure. Um, let's see. Did you have any other questions, Good Noodle?
No, not really.
Okay, fair enough.
Yeah, yeah.
What'd you guys go over in lecture yesterday? It was. I know you guys told me. I just forgot. What did you go over in lecture yesterday?
Um, yeah, I've forgotten as well.
Oh, no worries.
I think it was just more of, oh, so we did do something that I did want to talk about. Um, but I need to grab my notes. It was like when you add two hex and you have to like increment one value. Hold on, let me grab my notes. Unless Good Noodle, do you remember that part?
Oh, yeah, yeah, I think I know what you're talking about.
Yeah, one sec. So we went over like more syntax, like specifically if statements, like using branches and jumps.
Right.
We went through multiplication, but I want to say Dr. Harris said don't worry about division. But I can't find the crazy thing that oh, here we go. Okay, so is this it? It was, yes. So it was the generating 32-bit constants. I can actually, I don't know if you have like the slides in front of you
I just put it on the floor.
for chapter 6.
There we go. Sorry, give me just 1 second. Moving some stuff around.
Sure.
Okay, there we go.
Okay,
Sorry,
so it was,
so what was it that you were having trouble with?
yeah, it's actually slide number 39. It's some of the like load upper immediate, and like
Yes. So you said
we have to increment by 1. It was just, I was getting a little lost
you said it was
sauce there.
slide 89 or
39. Yeah.
13. Let's see. 11 of 32 phase 1. So this just happens to be like a quirk of the RISC-V architecture, the way that they implement the actual the processor hardware. That essentially makes it so when you do your when you write your code out, so in the example that's given on the screen, they mention a number hex FEDC8EAB, and they say, okay, we have one of our bits in that number, so it's bit 11 is the one they're referring to specifically, and on the next line of the code, they have load upper immediate S0, and then it's a number, FEDC9. And you'll notice that the 9 gets changed from the 8 we originally wanted. Because the whole goal of this code, according to that first line, is to have an integer which holds the value of that hexadecimal value. However, due to this quirk in the RISC-V architecture, there is one of the bits, like I mentioned, bit 11, so it would be, if I were to take that number they had, yes, that's right. And okay, so if I take this number and I ask myself, okay, how do I convert that to binary? I can do that for the B, not too badly. So that's going to be 0. 1, 1, 0, 1. So that would be B in binary. Then we have A, 0, 1, 0, 1. Then we're going to have E, 1, 1, 1, 0. Then we have, so this is that number, or the bottom 4 hexadecimal digits of that number in binary. And so what they're saying is, this is bit 0, bit 1, bit 2, etc. This right here is bit 11. And so what we know is that that bit is a 1. And so what we have to do, according to the architecture, is if that uppermost bit, bit 12 here, or bit 11, is a 1, then that means that if we want to use load upper immediate and get the correct value, for the top part of our code, which is the stuff after the 8, that would be the 8 CD. For those top 20 bits, we're going to have to increment that by 1. So it's not necessarily something that is supposed to be like intuitive or makes sense. It's just a quirk of the way that the processor is designed. And it's kind of just a rule that you have to remember whenever that 11th bit there is a 1, you have to take this value when you're trying to load an immediate, and you're just going to increment it by 1. That's pretty much all it's saying. And there's quite a few different things that you're going to be learning about that don't seem obvious at face value, and they seem like unreasonably complicated, especially when you guys get into the machine code translation. So when you're translating assembly into machine code, there's going to be some lines which, or some translations which have lots of the bits seemingly misordered and in weird places. And the reason for that is because the way that they order the bits means you could save on some piece of hardware, some sort of efficiency in terms of the processor design. And without knowing what it is that you're saving on, it makes no sense. And it's the same thing here. It's like, why? Well, that's just the way that the processor was designed, or the architecture is designed. And there isn't really much we can do about it besides just knowing the rule. So again, the rule is, if you have a number that you're loading, if you're loading an upper immediate number, so you have a really big number, and the bottom, typically they group the bits by 12 and by 20, because when you're doing a load upper immediate, that loads in a 20-bit number, and when you want to get the lower 12 bits, you just do regular add immediate. So what we say is, okay, if the add immediate number, the number we would do online, on that bottom line on the slide, the one that says add I S0 S0 minus 341, if that topmost bit would be a 1 when adding that number, then we just have to remember, okay, for the load upper immediate, instead of doing the number I wanted, I have to do one more than that. So I'm going to do another example for a different number. And let's go ahead and let's just do all A's. And so what you'd have to do here is you have to split it into the 12 and the 20 bits. So we say we want an integer A, or I'll call it the x, to be assigned to this value. And so the first thing we do is we say, okay, I'm going to load my upper immediate. So the upper immediate is this stuff. And I have to ask myself a question before I do that. I say, well, the bit right before I get to the 20 bits, is that a 1? And if we look at the binary expansion of A, it is. That 11th bit of this A is indeed a 1. So what I have to do is, instead of loading upper immediate all A's into my register, I'm going to load all A's and then a B at the end, because that's one more. So I would say load upper immediate, and then I would do, say, S0, 0. I'll do, S0, and then I'm going to be loading the hex value, all A's with. And then I'm going to take S0 and add something to it. I'm going to say add immediate, and I'm going to take whatever's in S0, I'm going to add itself plus, and then the bottom bits I have. Should put, actually. So again, this is going to be for any time when you're trying to do a load upper immediate, and the topmost bit of that third hexadecimal digit is a 1. You're always going to have to do this. So, like I mentioned, it's not supposed to necessarily make that much sense. It's very weird. It's a very weird quirk of the architecture, but it is something you would have to remember if you were asked to do something like this on an exam, or just in general if you're, what's it called? just in general if you're trying to write code. So now that I've mentioned it, I do want to point out that on the previous slide, so slide 38, it actually explains why this happens in terms of hardware. So with that in mind, if you guys want, I can describe why you have to add an extra one. Like why that's necessary.
Yes, I would like to know.
Okay.
Yes.
So the key point is that when you do an add immediate, so when you do add immediate, it's a 12-bit number, but your add immediate actually sign extends that number. So if it was negative, it's going to sign extend it to all Fs at the end, right? So if your number was originally AAA, what it's going to do is it's going to say, okay, I'm going to take that number, whatever that number was, and I'm going to sign extend it. But here the most significant bit is a 1. So that means I'm going to copy a 1 into all of the topmost bits. And this is the number that I'm adding over to whatever my register is. And so now we have to rethink what exactly happens as we go from here to here. Because in our heads, what we think is happening is we're supposed to have this number, the upper 20 bits of A's, added with the lower 12 bits of Y's. This is what we want to happen. However, since add immediate actually sign extends to preserve sign, actually what you're adding to this number up here is this, all F's. So, here's the fix. Instead of doing something in the processor, what they have is the actual, at the assembly level, you have to remember to code this. In order to effectively cancel out all those F's, we wanted to have zeros there, so we could add it directly and then we'd get the number, all A's. But we want to cancel out these F's. One way to do that is to add an extra 1 right here. And the reason why is because if we add a 1 to this F, it's going to become 16, so it's going to be a 0, and then you carry a 1. So I'll go ahead and do that off to the side, actually. So let's go ahead and add a 1 to that exact spot. Let's see what happens. Well, F plus 1 gets you to 16, so you have to write 0, carry the 1. And then again, F plus 1 gets you to 16, so you have to say 0, carry the 1. And you have to keep carrying this on until at the very end you actually get an overflow bit, which gets discarded because it's out of our bit range. But take a look at what's happened now. Now that we've added a 1 in this position, all of those F's have gone to zeros, and we're actually left with the original number we actually wanted to add on. We wanted to do 5 A's plus 3 A's at the end. And if we just add a 1 there, yeah, it gets rid of all the F's and we can do the addition we expected to happen. Now, you can't just add a 1 to this 12-bit number because when you encode it, it's actually just 12 bits, so you can't put an extra 13th bit at the beginning. The encoding just doesn't have enough bit space for that. So what you do is instead of adding 1 on here, you add 1 on the number above, which you can control because you have full control over those topmost 20 bits. So you can add 1 to this. And it doesn't matter which one we add 1 to because they're all going to be added to in the end. So just as a quick recap, the add immediate function takes a 12-bit input and sign extends it. So it takes a 12-bit immediate and sign extends it. When the top bit of that 12-bit number is 1, you sign extend a 1 to all of the top bits, and so they all become F's. But when we're actually adding, we don't want those F's to be there, we want them to be zeros. So we have to add a 1 to that bit 12 position. We can't add it to the 12-bit number because the 12-bit number goes from bits 0 to 11. It doesn't have a 12th bit to add to. So instead we add it to the other number, the one that was the load up or immediate. And so that's why whenever you do a load up or immediate and the 11th bit is on, you have to add 1 to the load upper immediate. So here, we would do this. And that would resolve our issue. When we add these two numbers, we should get all A's. And indeed, do A. B plus F. F is going to be 15 and B is 11. That's a total of 26. And so in hexadecimal, 26 would be broken up into 16, which is carried, and then a 10, which is A. And then 1 plus F is 16. Carry that over and keep it. 1 plus F is 16. A. 1 plus F is 16. So you carry that with A. 1 plus F is 16. You carry that with the A. And then this carry drops off. And so you get all A's. So it's very, very weird until you know why it is that you need to do this. It's because your add immediate doesn't just zero extend, it signs extends the number to preserve the sign. And because of that quirk of the add immediate functionality, to actually properly load an upper immediate, or load an immediate that's bigger than 12 bits, you have to add a 1 to that column. So I went through it. It's fine if you guys didn't get the whole process on through the first time. So would you like me to explain it again, or how are we feeling?
No, I think I got it now. I think the only question I had was why can't I got a little bit confused. Why can't we just add it to the last 12 bits that we have?
Yeah, that's a good question. So it has to do with the way you encode this, like in machine code. So you'll get to this soon. I'm going to erase all this actually. You'll get to this soon, translating assembly into machine code. But here's what we're going to do. So for an immediate instruction, they're called I-type instructions. And add immediate is an I-type instruction. You can tell because of that I there. It's add immediate. The I stands for immediate. Now, I'm going to try and do this off of memory because I don't remember the exact way that the bits are ordered for the machine code, but I do know that you are going to have, for any immediate function, you always have a destination register, a source register, which is typically just called RS, and then an immediate. And the immediate, like we mentioned, is 12 bits, so bits 11 to 0. So let's talk about how to encode this. In RISC-V, you have 32 registers. To encode 32 different locations to check for a register, you need 5 bits. So you need 5 bits to encode the destination, and 5 bits to encode the source.
Well, I didn't see you with the glasses, so there you go.
Now, that's a total of 10 bits to encode which register we're selecting. And we also have 12 bits for the immediate. The total instruction encoding, if I recall correctly, and I may be wrong, should be 32 bits. So I'm going to go ahead and pull up a diagram, and I'm going to use that just to verify what I'm saying is correct. So, let's see, RISC-V, I-type machine code. Let's see. Oh, goodness. I-type, 12-bit immediate. Yeah, okay, that's right. So, there are a total of 32 bits in the entire encoding. 10 of them are used up, 5 for each register encoding. 12 of them are used up to make the immediate. 7 bits and 3 bits are left over and split into 2 categories. So there's a total of 32 bits. I've used 10 and 12, so that's 22. So 32 minus 22, that's going to be 10 left. And I split them up into these 2 groups. The 7-bit group is going to be for what's called the opcode. And generally, the opcode is just basically determining what instruction we're doing. So for an opcode, all zeros, maybe you're doing add immediate. For an opcode, all ones, maybe you're doing OR, something like that. And for some instructions, there are a lot of instructions. And so what we have for these last 3 bits is what's called a funct field. There are so many instructions that you don't have enough space in 7 bits to record them in opcode. So you sometimes group instructions together in like similarity. So maybe you'll have 3 of the arithmetic operations. Maybe, let's just say addition and subtraction. Maybe addition and subtraction have the same opcode because they're both, very similar, related arithmetic operations. And to determine which one we do between those, we specify a different function for each. And so this funct field is called funct3 because it's 3 bits. Now, you're going to get into this a lot soon, but the basic premise is when you physically encode this, when you store this in program memory, you only have 12 bits to store for your immediate. You don't have any more bits. There's just no more space. And so to answer your question, this is bits 11 to 0, and we're trying to change bit 12. But there's no extra 33rd bit for us to use. There's only 32 bits, and they're all already being used. We don't have extra space to make this 1 bit wider. It's encoded as a 12-bit value. We can't make it wider. So that's the reason why we can't just say, oh, let's add it on. That bit value isn't even present in this machine encoding. It is present, though, in the, in the load up or immediate encoding. Because for the load up or immediate encoding, the immediate is actually a 20-bit value. And so for the 20-bit value, that bottommost bit, that is bit 12. And so you can just add 1 to that, and then it works. And I mentioned that it gets sign extended, this 12-bit number. That's where the Fs all come from. The Fs aren't encoded in the actual machine code because you can just have a separate module, a separate unit, just read whatever the bit 11 is. So it's going to read bit 11, and then it's going to duplicate that into the topmost bits and then send that to the ALU for addition. So you don't actually have to encode it in the machine code. Okay. Does that... Well, how are we feeling about that? I guess is my question.
Yeah, I think I feel pretty good. I just didn't realize, I wasn't sure what was going on. So now I know that if I'm ever doing, the load upper immediate, I just need to convert my hex into binary, check that 11th position, and then if it's 1, do what we did. So
yeah, and you don't even have to convert it to binary if you don't want to, because all you really need to do, right, is you look at the number, and for the 8-bit hex number. Oh, sorry, did you have a question?
No, yeah, I see. If it's A through F, it has to be a 1 on there.
Even more if it's 8 through F. Or did you say 8 or did you say A?
Oh, no, I said A, but yeah, you're right. If it's 8, because we have 4 bits.
Yeah, that topmost bit is 1. So if that 4th hexadecimal digit, or the 3rd hexadecimal digit, is any number bigger than 8, then you automatically know you're going to have to add 1 to your load up or immediate.
Yeah, that's probably a really good, trick to know for the test, to just do it quickly instead of converting, so...
Any other questions?
In your example, when we were load upper immediate, and then
From 6 to...
Okay. All right. Well, I guess I'll get out of here.
Sorry.
Yeah, no worries. I just didn't know. What's the event for?
For college of engineering.
No, but what's the event? I mean.
It's public farming.
Oh. Okay. Cool.
Thank you so much. Have a nice
No
day.
worries. Yeah, you too. All right, you guys. I'm getting kicked out.
Okay. Yeah, no problem.
I'm gonna go ahead and pause the recording and get stuff moving.
Oh, are you gonna jump back on? Or are you done?
I'm gonna run over somewhere else where I can have a whiteboard. I'm probably gonna run up to upstairs TV. I'll probably be ready in about 5 minutes. You can stay in the Discord if you want. I'm just gonna close my camera off. Okay, there we go. So I unpause the recording. Yeah, so basically for that immediate encoding, you have 10 bits, 5 for each register that you're specifying, 12 bits for the immediate value, and then you have another 10 bits to basically say, this is the function I'm doing. This is the instruction I'm implementing. 7 are in the opcode and 3 are in the func3 field. And so just generally speaking, you have groups of similar instructions that may have the same opcode, but have different funct fields or func3 fields, so that you're able to decide between them and figure out which it is that you're actually doing. Yeah, and so again, the reason why we said that you couldn't just add the extra one onto the 12-bit number is because it requires that 13th bit, but the 13th bit isn't present for use in your machine code encoding. There just isn't an extra bit to go around. And so that's why you have to instead add it to the value in the load upper immediate, because the load upper immediate encodes the 12th bit position. And so you can actually add to that position there because it's actually within the encoding. And then I also mentioned that, because you can sign extend in the processor itself, you don't have to encode that for the 12-bit value from the add immediate. Because you can sign extend in the processor, you don't have to encode the sign extended value in your program memory, so you get to save on space. Okay, so with that out of the way, do you guys have any other questions for me?
So if we had all Fs, and then we were to do a load upper immediate, that would just all turn to zeros, right?
If we had all Fs and we tried to do load upper immediate, that would be well. So are you saying you want to at the end you want to get all Fs? Is that your goal? You're saying?
And I was taking a look at what your example with how we have our load upper immediate. We want to increment our 12th bit by 1.
Right.
But what would happen if they were all Fs? So wouldn't that just go back to a 0, and then that would increment? We would carry over a 1, and then so our next F will be would add a
Like
a 1 as well.
If the upper immediate value was all Fs, is that what you're referring to?
I think so. Yeah.
Yeah. So think of it this way. Yeah. If you add a 1 there, it's going to carry, and basically that entire upper immediate value is going to become 0, right?
Yes.
But when you do the add immediate, remember that gets sign extended. So while the load upper immediate all goes to 0, so it basically doesn't do anything, the add immediate itself sign extended, and now all those Fs are present. So actually, if you were trying to do something where all those top 20 bits were Fs anyways, you would just say add immediate and then the bottom 12 bits that you care about, and then you're done, because it automatically sign extends the Fs for you.
I see. Thank you.
Yep.
Oh, yeah. So instead of LUI, like S1, comma, hex 0000000, and then add immediate A, you would just do add immediate with your A's.
Yep.
Okay.
Exactly.
Well, that was a good question. That's very interesting.
And that's how it works, right? When you say, I want to add immediate -1, and you think, okay, cool, that's great. And then you think a little harder and you're like, wait, how do you encode -1 again? That's all Fs. So are you saying I have to do an add immediate 3 Fs and then a load upper immediate 5 Fs? Well, no, because it gets sign extended, those bottom 3 Fs. So they all become Fs. Let's see. Yeah. Any other questions for me? Oh yeah, go ahead.
Oh, sorry. Could we take a look over a little bit of multi-ported memory? Like, what type of questions that would we expect with that?
Well, for multi-ported memory, that's just saying like, so multi-port literally means many different ports or more than one port, And so you could have like single ported memory where you use the same wire to read and write. So, you know, you have a unit of memory. When you're trying to write to that memory, you basically send a signal to the what's it called? To the memory to tell it go in read mode, and so that wire is going to be an input wire. And then when you're trying to read from the memory, you tell it to function in the other mode, and so that's going to be an output to your ALU. So that'd be single ported. Multi-ported just means that you don't have to have one wire do multiple functionalities. You could have one wire be for inputs and the other wire be for outputs. So that's multi-ported memory. And in fact, I don't know if you guys will be talking about how like the register file and how the program memory like visually looks, but in the RISC-V processor architecture you guys are talking about, at least in the textbook, it is a multi-ported memory. So in terms of questions you'll be asked, and I think it is a multi-ported memory, I'd have to check, but I'm pretty sure it is. In terms of questions you'll be asked, I'm not really too sure what questions she would even ask you about multi-ported memory stuff. Why do you bring that up?
Oh, it's just because I saw it on the slide, so I thought like we might go over it, and
You might talk
it
about
might
it
be on the
briefly,
test.
but I doubt you'd see like any homework questions or quiz questions or exam questions on that specifically. It's just like the general idea of it.
I see. Thank you.
Yep. Any questions for me? There we go. I cut out a little bit. Let me. Yeah, my volume reset too. Cool. Yeah, you guys have any other questions?
Going back to the multi-port, so that would be a form of parallelism, right?
You mean like being able to read and write at the same time, since there's
Mhm.
multiple ports? Yeah.
Yes.
Yep.
Okay. And then with single port, that would be more concurrency.
It's not concurrency. It's just sequentialism. You can't do both at the same time, so you have to do one and then do the other.
Oh, I see.
I'm gonna actually take a look at your guys's next. Well, I'm gonna take a look. She's posted the slides for chapter 6, which is the one about all that stuff. Do you remember how far you guys got in the slides? Was like 39 as far as you got, or was it farther than that?
No, we got farther. So we got to hold on. So we got to like 62 for loops. We didn't do less thans yet.
Okay. Okay, well, you'll get to less thans. It's a very small section. The next like big chunk of stuff is going to be arrays and how to make arrays in assembly. So it's not too bad. I think I mentioned this a little bit briefly before. You basically take a bunch of contiguous memory spaces, which is to say they're all one. The addresses are all one right next to another. And so you have one as your kind of base, the start of your array. And every value after that for a specific amount of values, so say you have an array of size 10, you would have your base address at, 27. Well, 27 is not a reasonable number. 28. Hex 28. And then from there you would say, okay, well, now I go to hex 2C, and then I go hex 3, 0. And then I go hex 3, 4, hex 3, 8, and so on. And all of those are your next values in the array. And so the way that you access them, say in like high level code, is you just say array at address 7. But what that's doing actually in assembly is you would take the base address, which is the address at index 0, and then you add an offset. And the offset that you add is just basically how far away you are from index 0. So if you're looking for array index 2, you would have your base address, which is where array index 0 is stored, and then add 2 jumps, whatever that jump size is. For this architecture, it's units of 4. That's how much our addresses jump by. So you'd say plus 8, or basically 2 times 4. And the 2 comes from, well, it's index 2 that we're going for. In general, it's always going to be n times 4, where n is the index you're trying to access. And the 4 can change, again, depending on what processor architecture you're referring to. If it's not byte addressable, if it's just a word addressable, then it would be 1s. And if it was, I don't know, nibble addressable, it would be 8, but that's not really a thing. So that's pretty much all I have to say about arrays. I did mention that a little bit last time, but I thought I'd bring it up again.
Wait, can I ask you a question? I'm just going through the homework answers.
Yep.
Okay. For homework 12, I don't know what I'm doing wrong here. So for 3A, I'll let you get it up. I don't know if you have it in front of you.
I do not. Let me go ahead and pull it up. You said it was 12.3a or homework 12.3a?
Yeah, homework 12, and then my question was 3A.
Okay.
Okay,
I got
so
it up
I
here.
get
So what's the question?
y equals -10, but why did I get for my hex, I got hex 16 for -10. Why is it, I get that it's sign extended
Mm-hmm.
with all the Fs, but oh, is it because F is -1?
All F's
Is
is
that,
-1, right?
yeah, okay.
So if you were to try and encode -15, remember that the way you even say I want registers S4 to store -15 is you say add I S4, comma, the 0 register, comma, -15. But how is -15 encoded? It's a whole bunch of F's and then a little bit stuff different at the bottom. And the stuff different at the bottom would be, I think, a 1. That sounds right in my head. So it'd be hex, all F's, and then a 1 at the bottom. That would be how you encode -15. And then if you add 5 to that number, well, hex, all F's, and then a 1 at the bottom, plus all zeros with the 5 at the bottom, well, the 1 plus a 5 is 6. And the F's all added with a bunch of zeros remains F's.
Wait, I'm so confused.
There you
Oh
go.
no. I think
Let me draw it up.
okay, yeah. I thought I understood this and now I'm really doubting everything.
Is that too small? It's fine if it is. I can move the...
Yeah, it's kind of hard to see, sorry.
No, you're good. Alright, we're gonna go on an adventure. Let's see this over here. Okay, I know it's tilted. Is that second 15 big enough, or can you not see it?
Yeah, the only problem is it's about to go into a big glare of the light. Yeah, okay, down there is perfect. Thank you.
Okay, cool. So -15 we want to write in 32 bits. So what we do is we say first find 15. 15 is going to be hex 0, 0, 0, 0, 0, 0, 0, F. Because remember, F means 15 in hexadecimal. And because it's a positive number, we have a bunch of zeros up here. So now the next thing we do is we say, okay, I want to negate this. So I'm going to do the reverse the sign, which is you flip all the bits. So all these zeros become F's, because you're flipping all the bits from zeros to 1. And then this bottom one becomes a 0. So remember, you flip all the bits, then you add 1. So I'm going to take this, I'm going to add 1 to it. And that's how you represent negative 15. So are we cool with that? That first part? Does that seem reasonable?
Yes, except like I think what I'm getting confused about is like I'm just thinking of doing it the normal way where I put everything into binary first
Okay.
and then switch it to hexadecimal.
So that's how you'd represent 15 in binary, where it's 28 zeros and then 4 ones at the bottom, because this is the number 15. Are you cool with that?
Yes.
So these two are the same thing, and I can do the same thing I did here. If I flip all those bits, then I get 28 ones. And then these bottom bits also get flipped to zeros. Except for the last, because I have to add 1 to it. So I flip all the bits, and then I add 1 onto it.
Okay, I see where all the F's with the 1 is coming from now.
So that bottom 4 is the 1, and then all 1s is all those F's up there. Yep.
Yeah, okay. That makes sense now.
Okay. So now you have to take this and you have to add 5 to it. And so we think, okay, you're doing add immediate, or sorry, you're doing add immediate with 5, or whatever it is. You start in a register and add the 2 registers. Doesn't matter. At the moment, the value 5 is stored as all zeros with the 5 at the end. So a bunch of zeros. And so now we add those two numbers together. 0, 0, 0, 0, 0. So you take those values and you add them column-wise. So 1 and 5 make your 6. And then you just bring all your F's down. And so that's how you get all F's and then a 6 at the end. And now I'm facing away from the microphone while I was talking. Could you guys still hear me while I was explaining that?
Yeah, so I think where I went wrong, if I said hex 1, 6, my problem was that I didn't sign extend it. And if I sign extend it, all of those 1s will just become an F. The
Correct.
4 1s will become an F.
Yes.
Okay, I got it. Thank you.
All right, cool.
So with this, we always need to sign extend it.
Yes.
If it's a negative number. If not, I think you said it's implied, like you can just drop all those zeros.
Yeah, so it mostly depends. If you're doing like add immediate and you're doing a negative number, yeah, it's always going to be a bunch of F's at the top. But in general, the way to like guarantee if you're trying to do add immediate, is you just look at the 12 bits that it's encoded as. So you look at the 12 bits and you just ask, is the top bit a 1? If it is a 1, then it gets sign extended. If it's a 0, then it does not get sign extended. It still gets sign extended, but it's going to be all zeros instead. So if you just look at that topmost bit of the 12-bit value, that'll tell you whether or not it's all F's or all zeros above. Any other questions for me? No? No other questions? That's fine.
I'm going through the rest of the homework really quickly. I'm sure I did something else wrong.
Yeah, no worries. Let me go and erase that actually. What about you, Good Noodle? Got any other questions?
I was taking a look at the homework solution, and I just realized that I completely forgot about stating what y was.
Ah, yes.
Yeah, so but aside from that, I mean, it makes sense so far. Of like what you said with sine extension, and then yeah.
Okay, good. Glad to hear that.
So, really quick question. For like, for example, what is this? Number 3B
Yeah.
in the code. So, here I see it. The first line is add I S30 hex 42. For some reason, like I converted this to 66, and so mine was add I S3066. Would that still work, or am I like messing with the address?
No, that'd be right.
Or
Because
okay,
you did you put 66 or did you put hex 66?
I put 66
Then that's fine. Yeah.
numbers.
Because
Okay,
when you just put a number, it assumes it's decimal. And since decimal 66 and hex 42 are the same number, it'll work.
okay, cool.
We could do both though, right? We could do either hexadecimal or decimal. It doesn't really matter.
Could do either one. Yeah. I'm trying to think. The only problem you'll get into is if you're trying to do add immediate, you have to remember that the number is only a 12-bit number. You can't go any more than 12 bits. And so you couldn't, for example, say, I want to add 9,000 and something, because that overflows your number of bits that you have available for add immediate. So if you're trying to go for a super big number, you would have to write out load upper immediate for the upper part of that number, and then for the bottom part, you would have to do the add immediate. In which case, you might as well just convert it to hexadecimal because it'll be way more difficult to try and do the math in decimal. Though I will say that if you do actually write add immediate S30 and then some really big decimal number, actually, as long as you do it such that that decimal number can be encoded in 32 bits, it will work, but not as a proper instruction. It'll be a pseudo instruction. So it'll take that and then break it down into a load upper immediate, and an add I. But when you do that pseudo instruction, you wouldn't say add immediate, you would say load immediate. So the pseudo instruction is LI, load immediate. It's not a real instruction. It gets replaced with an add immediate followed by a load upper immediate followed by an add immediate. So it's a pseudo instruction.
I see. Thank.
Yep. All right. Any other questions for me?
With pseudo instructions, is it like shared among every single type of assembly, or is it specific as well?
So pseudo instructions, I'm pretty sure there are pseudo instructions for most assembly languages. Obviously, the instructions which are pseudo instructions are different depending on the assembly language, but that like the theme of having a pseudo instruction is common in a few of them. As for like how they're done, again, they're not done at the processor level, they're done at the assembler level. So when the assembler is reading your assembly code, it's going to see your pseudo instruction and break it into one or more real instructions. And what's it called? And that's how it's implemented. It's not actually a real instruction run on the processor, which is why it's called a pseudo instruction. You can still type it, but that's not what gets executed on the processor. All right, so it's just a little bit past. Let me actually check my phone. I think my computer time is wrong. No, it is. So it's just a little bit past 6:30. Did you guys have any other questions before I call it for today?
for me. Thank you.
All right. You're very welcome.
Not for me either. Thank you.
Both very welcome.
See you tomorrow.
See you guys tomorrow.
Bye.
Thank you. Bye.